The differential form of the fundamental laws, tutorial number 10. Consider steady, inviscid, incompressible uniform flow in a two-dimensional diverging channel as shown in the figure. The inclined wall of the channel are straight and the fluid enters the diverging section with velocity v1 equal to 40 meter per second. Given h equal 1 meter and assume unit width. Determine an expression for the velocity component u as a function of position x along the channel. We assume that u does not depend on y, and we need to determine an expression for the acceleration of the fluid in the x direction. So in this situation, we have a diverging section like this, and we have the height of the inlet section here is h, and the height of the outlet section is 4h, and this is the axis of x direction, and the length from here to here is equal to 10h, and the height of this inclined section is given by hx, h of the function of x. For A, we need to determine an expression for the velocity component u as a function of position x along the channel, and we assume that u does not depend on y. So in these problems, we assume that it is a steady flow, an inviscid flow, it is incompressible flow, it is uniform flow, and only two-dimensional is considered in this problem, and we take it as per unit width, or we assume that the width of that converging section is equal to 1 meter. We could calculate the volume flow rate at inlet by using this equation. Because it is incompressible flow, so we could calculate it by Q equal to AV, and the cross-sectional is 1 times 1 because the height of H here is given as 1 meter, and the width here is 1 meter. And the velocity at inlet, V1, is equal to 40 meter per second. We could get the volume flow rate at inlet is equal to 40 meter cube per second. And then the cross section at the converging section here is increased. So we could say that the cross sectional area at the increasing section, converging section here is 2hx, means this hx times 2 to get its total length times the width of the converging section. However, for this calculation, we take width of this is equal to 1 meter. So the cross-section area at the converging section here is 2hx only. However, the value of hx is keep increasing along the axis here. So we need to determine the function of hx. To determine the function of hx, we can first draw a graph to represent the increasing of this converging section. So we take the origin here at the midpoint, at the center point of the inlet. So we could take coordinate for this point is equal to x equal to 0 and y is 0.5, because the total height of h here is equal to 1, and the height equal to 1 is given in the question. So we take coordinates for this point is 0 and 0.5, and then here at this coordinate we take it as 10 and 2, because we already know the value of h here is 1, so we could take the length of this area is equal to 10. So the coordinate is 10, and the 4h here will give you 4, but the x-axis here is actually at the center point, so the total height here is actually equal to 2. So the coordinate of this point at here is equal to 10 and 2. So we could represent this line as the inclination of this converging section. So we could have the equation for this linear line, this straight line, by the general equation of hx equal to mx plus c, which is the m here is the gradient of this line, and c here is the cross-section point at y-axis, in this case at hx axis. So I assume that you already know how to calculate the linear graph from this graph. So we calculate it. We could say that this line is equal to hx equal to 0.15x plus 0.5. So, and then from the equation of flow rate, Q equal to AV, and we could rearrange as V, or to be specific, we take it as U because we only analyze for U direction, velocity at X direction. So we have U here is equal to Q over A. Q is already calculated, it is 40 meter cube per second, and A is equal to 2hx, and we substitute the value of hx here by 0.15x plus 0.5, and then we could simplify it. We could say that u, or the velocity along the x-axis, is equal to 20 over 0.15x plus 0.5. So to determine an expression for the acceleration of the fluid in the x direction, we could have the acceleration equation at x direction is like this. Because we are focusing only on x direction, so we could cancel all parameter that not related to x. So we have ax, acceleration for x direction, is equal to u del u over del x. So we know the value of u is 20 over 0.15x plus 0.5. We could substitute in here. So to make a simple calculation, we assume that S is equal to 0.15x plus 0.5. So we could differentiate it. ds dx is equal to 0.15. And now we could rewrite u is equal to 20 over s. And then we could calculate du ds is equal to minus 20 over s square. So to get du dx, we could calculate by multiplying du ds times ds dx. We already calculate du ds is equal to minus 20 over s square, and ds dx is equal to 0.15. So we could get du dx is equal to minus 3 over 0.15x plus 0.5 square. So we could calculate the acceleration at x-axis here by using the basic equation u del u over del x, by multiplying these two values to get minus 60 over 0.15x plus 0.5 cube. And then let's say we have an additional question for this one. For example, if we need to determine the expression for the velocity component v and the expression for the acceleration in y direction. So how to solve this one? We could do like this. So this is the answer to get the expression for the velocity component v. From the continuity equation, we know that du dx plus dv dy is equal to 0. And then now we need to calculate the velocity component of v. So we could rearrange these terms into dv dy equal minus du dx. So what we need to do next is we integrate both sides, left and right here, with dy. And we could write as this one. So integral dv dy with dy can get v, because we could cancel the value of y here, and integration of dv will give us v. And we do the integral for the right hand side. We have negative integrate of du dx dy plus c is the constant. So to solve this one, we need to do step like this. From the previous result, we know that du dx is equal to this one, minus 3 over 0.15x plus 0.5 square. So we substitute the value of du dx here in this term. So we get the integral of minus 3 over 0.15x plus 0.5 square dy plus c. And we could calculate, we could solve this term towards the dy here, the integral of dy. So we have a new y here, and then negative is become positive because we have a two negative sign here. So the v now is equal to 3y over 0.15x plus 0.5 square plus c, and c is the constant. We need to determine the value of the constant here, so we substitute with the boundary condition. We know that the v is equal to 0 at y equal to 0, and it makes c, the constant, is equal to 0. So we could get that v in the function of x and y can be written as 3y over 0.15x plus 0.5 square. For the second question, to get the expression for the acceleration in the y direction, we could say that the equation for acceleration can be written like this. So this is the equation for the acceleration at x direction, and this is the equation for the acceleration at y direction. So there are no major changes that you could see here, unless except of the value of, for x direction we will use u, all the parameter here, and for y we use v to represent the velocity along the y-axis, and it keep repeating the del t, del x, del y, and del z. And because we don't have the velocity for w here, so we could neglect the terms of w, del v over del z. And then they are steady flow, so the dv dt is equal to 0. So we could say that the acceleration at y-axis is u dv dx plus v dv dy. So I change from the partial differential del v del x here into dv dx, because there are no partial differential need to be used at this moment. So from the previous calculation, we know that u is equal to this term, and for the last calculation we could get the value of v. Then we could differentiate this term to get dv dx, and we get dv dy. So and then we substitute all these parameter, all this term, into this question, into this equation. We have u, we have v, we have u, we have v, and we have dv dx, we have dv dy. Everything is calculated here. You could get that acceleration at y direction is minus 9y over 0.15x plus 0.5 by the power of 4.